I think we can start the webinar. Bapak Ibu sekalian, sepertinya kita sudah bisa mulai webinarnya. Selamat siang. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Kembali lagi kami dari Ikatan Alumni Teknik Metalurgi ITB. Pada hari ini kita akan mengikuti webinar yang ke-8. Hari ini hari Jumat tanggal 16 Oktober 2020. Dan hari ini kita akan mendengarkan presentasi terkait dengan copper flash smelting. We do have a presenter from Finland, Mr. Pekka Taskinen. It is great honor for us to have Pak Pekka to be presenter in this topic. He has a lot of experience in this flash smelting. So ini kesempatan yang sangat bagus buat kita semua untuk mendengarkan presentasi dari Mr. Pekka. Sebelum kita mengikuti presentasi dari Mr. Pekka. Jadi nanti akan ada 2 presenter pada hari ini, Bapak dan Ibu sekalian. Yang pertama adalah Mr. Pekka dan yang kedua adalah Pak Imam Santoso. Jadi nanti akan ada 6 topik yang akan disampaikan dalam webinar ini. Nanti akan kombinasi dan juga kita akan kombinasi antara bahasa Inggris dan juga bahasa Indonesia. Sebelum kita mulai, saya ingin memperkenalkan atau membacakan CV Profesor Pekka. Profesor Pekka, nama full name-nya adalah Taskinen Pekka Antero. Kemudian untuk pendidikannya Doctor of Science dari Helsinki University of Technology. Kemudian Master of Science-nya juga dari Helsinki University of Technology. Saat ini beliau merupakan Professor of Material Science di Metallurgical Thermodynamics and Modeling, Aalto University. Kemudian September 2015 sampai 2016, Desember 2016, beliau merupakan Deputy Head of Department Material Science and Engineering. Itu adalah presenter pertama. The first presenter is Profesor Pekka, and then the second presenter atau yang presenter yang kedua adalah Bapak Dr. of Science Imam Santoso, ST Master Filosofi. Pendidikan beliau doktoral dari tahun 2014 sampai 2019 di School of Chemical Technology, Aalto University, Finland. Kemudian Master of Filosofinya tahun 2011 sampai 2013 di School of Chemical Engineering, University of Queensland, Australia, dan Bachelornya tahun 2003 sampai 2007 di Department of Metallurgical Engineering, Bandung Institute of Technology. Saat ini Pak Imam merupakan dosen di Department of Metallurgical Engineering, Bandung Institute of Technology. Itu merupakan summary dari CV kedua presenter. Sebelum kita lanjutkan ke presentasi, mungkin ada beberapa hal yang perlu kami sampaikan Bapak dan Ibu semua terkait dengan tata tertib. So the general rules untuk presentasi ini, yang pertama adalah gunakan nama akun yang formal dan berkomunikasi menggunakan bahasa Indonesia dan bahasa Inggris yang baik dan benar. Kemudian dalam webinar ini tidak diperkenankan untuk berbicara politik, gosip, obrolan berbau sara, atau obrolan yang tidak bermanfaat lainnya. Kemudian peserta mengikuti instruksi dari moderator selama kegiatan ini berlangsung. Kemudian peserta aktif menyimak sepanjang jalannya materi dan wajib memute mikrofonnya. Setelah pemaparan materi, moderator akan mempersilahkan peserta untuk bertanya dengan menggunakan fitur chat room atau juga raise hand. Dan di akhir acara, peserta dan narasumber akan melakukan sesi foto bersama. Hal-hal lain yang belum diatur di tata tertib ini akan disampaikan kemudian. Mungkin itu sedikit general rule-nya. Tanpa berpanjang lebar, saya akan persilahkan Profesor Pekka untuk menyampaikan presentasinya. Profesor Pekka, time is yours for presentation.
I will try to share my screen with you and start with this rather long slideshow, which we prepared together with Imam. So greetings from Helsinki. We are in the bright morning of typical kind of Finnish fall, where temperature is probably 20-25 degrees lower than in Indonesia just now. So it's time when we are waiting for snow in this country. So just for your information. But I will talk today about flash melting, and we have divided with Imam this talk into 6 sections, which deal with flash melting, its history, and practicalities in running a flash melter, and then downstream processing of matte and fire refining of matte, as well as flash converting, continuous solid matte converting. Then we tried to scan some future trends and needs in copper smelting and flash melting area. And finally, Imam will conclude this talk with some words. So first, because this is the first copper webinar of ITB, so I decided to include some historical background into this talk, and flash melting, as it was invented in Finland some 70 plus years ago. So it has some interesting features which may be of use in understanding some issues which become later. So flash melting is an invention of late 1940s, but its basic and fundamental areas were patented and presented already much before that. And what is the actual invention of this Finnish company Outokumpu, who put the idea into industrial use, is really industrial large-scale operation of a first flash melter, which was done in Harjavalta, Western Finland, in a smelter which now is called Boliden Harjavalta. And since that, 57 flash melting plants have been built and delivered to customers, and out of those, few have been closed by now for various reasons. So what is the essential feature of flash melting and flash converting is that it generates its energy by itself. So the heat balance of the operation is the key to run the furnace on a continuous basis. And it is often described with such diagrams which tell on the left-hand side the reaction heat and generated as a function of matte grade and the various flows of energy needed for heating up and maintaining the process temperature in the furnace for matte, slag, gases, and heat losses. And this is the core of running flash melting. This is what you have to keep it going on a continuous basis. So it is self-sustaining, and you need to keep it running that way. So another very important characteristic feature of flash melting furnace is that all these processes ensuring the operation, they take place in a single location of the furnace, in the reaction shaft, where all heat generation is essentially taking place. And also pure technical oxygen can be used in flash melting. So there's no limitations in that respect in the technology. So why this technology has been successful, so that in 70+ years, more than 50 furnaces have been built. So it's based on closed furnace design, reliable auxiliary equipment, and very much increased specific capacity since the very beginning. And this is a result of continuous R&D development of first flash melting by Outokumpu and Outotec. So another feature which may be minor in some opinions is that flash melting, flash converting smelters and DON, direct Outotec nickel smelters, don't have grains. There is no ladle transport of material, which technically allows easier scheduling of the smelting operation without fumes from ladles and launders. What that means in practice, or has meant in practice, is that sulfur capture in flash melting operations has been very high. The data comes from Brook Hunt. It's not Outotec data, but it comes from Brook Hunt. And this graph shows the sulfur capture and its development from early 1990s to 210, and it shows that the sulfur capture has been in flash melting processes more than 90% all the time, whereas the other technologies, even they have been improving their share in this sulfur capture to sulfuric acid has been rather low 30 years ago, and it's still much lower today than flash melting. And this autogeneity, the capability of collecting chemical energy from the sulfide concentrates, means that there's very little external energy, fossil fuels used, and that means that the carbon footprint of flash melting has been always very small, going down along the years, but compared to other copper smelting technologies, this gap is between 30 and 40%. So these have been always good sales arguments for the technology, and they still are that. So what is the result of the originally selected furnace vessel design and the operation of flash melting? So no leakages of SO2 to external atmosphere, low fugitive emissions to the on the site, and good in-plant hygiene and best environmental performance amongst various copper smelting technologies. My colleague and friend at Outotec calculated some years ago what this has meant in the world for the climate and atmosphere of the globe. And this calculation is also based on Brook-Hunt data, and it is showing that since about 1970, if copper would have been smelted with old-fashioned conventional technologies only, the emissions to the atmospheres would have been going along this red curve. And in reality, they have been going along this blue curve. And this is the sulfuric acid amount, which has not been emitted to the atmosphere. It's over the period of 1970 to 2010. It's almost 100 million tons of sulfuric acid, meaning 50 million cubic meters of sulfuric acid. So that is a huge amount of ingredients for acid rain in industrialized sites and only from copper smelting. So what is I promised to tell you some historical development in flash smelting. What is the kind of development path from 1950s till about next millennium, early next millennium. So we had first process preheating, which was converted into strong oxygen enrichment. Then came direct to blister flash smelting and flash converting, and further on some refinements of these technologies. So what we had there was in a big scale development was significant increase in smelting capacity in furnaces which were built before, direct smelting of blister copper with adjustable sulfur content in one furnace, and continuous converting of solid matte to blister copper. So these are the major achievements in flash smelting. And for those purposes, also a lot of advanced R&D tools were adopted in Outotec's activities from 80s. Computer-assisted thermochemistry was in use, so computational thermodynamics for fluxing and smelting simulations from 90s onward, and around the same years also CFD, computational fluid dynamics, and its more advanced forms were adopted for more traditional scale modeling and replacing time consuming issues in developing new process vessels and equipment. And this ended up with along with time in increasing number of copper smelters and nickel smelters using flash smelting. And this graph shows the early stages of increase in smelting capacity by the flash smelting technology, and later on by the flash converting technology. So the cumulative total capacity in the world by flash smelting has increased all the time, and today it is more than half of copper which is produced by flash smelting furnaces and technologies with its various variants. All right, this was my lengthy introduction to you about the history and kind of boundary conditions where copper smelting was struggling in decades from late 1940s till today. So let's step now into issues dealing with matte smelting in flash furnace. And this slide on left shows a cross section of a flash smelting furnace, which is really divided into three parts. We have a reaction shaft here and settler part connected with it, and then uptake for gas outlet. And the right-hand side explains to you that flash smelting is the BAT, best available technology by EU in the field of copper smelting. So it is recommended by formal authorities here in Europe as the technology for copper making. As I pointed out earlier, reaction shaft is the key energy source in flash smelting. So it is about 10 meters high, hollow cylinder, vertical cylinder, where raw materials are fed. And chemical reactions take place mostly in here in the reaction shaft, and its specific feature is that all free oxygen which is fed is consumed from the gas on the level of the settler roof here. So there's no O2 molecules left in the gas. Everything has been consumed by the oxidation reactions of the copper sulfide minerals. Small fraction of external energy, as shown in this graph, is sometimes used in flash smelting, depending on the concentrate grades and depending on the needs to keep the off-gas temperature on a certain temperature level. But essential is that matte grade produced by the furnace can be controlled over a wide range of matte grade, and it is up to the downstream processing what matte grade flash furnace is actually producing. So we control the matte grade by adjusting the oxygen coefficient of the reaction shaft. This oxygen coefficient, which is defined by total oxygen volume, pure oxygen, for each ton of feed mixture, is specific to every mixture and the target mat grade. So that can be adjusted independently in most cases from the adjustment of the heat generation, which is important. And as we will see later, the flight time for the concentrate to fall from the top of the reaction shaft to the set is long enough for allowing this kind of mat grade adjustment. As I said, all oxygen entered and introduced in the reaction shaft is captured by the concentrate and its oxidation reactions during that flight of the particles. So reactions take place in gas-solid liquid suspension, and there's only 2 to 3 seconds, as we have estimated, for each particle to react and to be heated up and ignite and capture the oxygen from the gas. This requires fine and dry feed material in order to secure ignition of the particles. So, to summarize, what I just said is it can be done in such a way that the reaction shaft completes the oxidation reactions of the sulfide minerals. The matte making and slag making reactions, the final assay of matte and slag is generated in the settler, which also acts as reservoir for the melt, so waiting for tapping. And off gas coming from SO2 rich off gas coming from reaction shaft is led to the uptake and further on in the gas train, which is composed of heat recovery boiler, ESP, and further on blowers and acid plant. So flash smelting is very flexible in terms of its raw materials. And it is evident that because we are dealing in heat generation, we are dealing with enthalpies, reaction enthalpies of oxidation reactions. It is not enough to know chemistry of our feed mixture. We need to know also mineralogical assays of our concentrates and other raw materials for calculating correctly the reaction enthalpy. So otherwise we are not sure how much energy is generated or required by the components of the feed mixture. It is sure that all sulfides ignite and produce heat in the reaction shaft. That is what we know from various fundamental and practical tests and measurements. this means that we have
Mr. Pekka, I think you are muted.
Am I online now? Can you hear me?
All clear, Pak?
Yes, Pekka, we can hear you.
Okay, so sorry for that. So there's one pipeline, so to say, from raw materials to the anodes in flash melting. So the reliability of each unit is essential, and no kind of bypassing of the process is possible except in the case which is now coming into Indonesia, where you will have flash melting, flash converting furnace. So the solid matte storage may act as a buffer between smelting and converting to a certain degree, but it's not for long-term buffering at all. So how we combust, or how we generate, how we combust copper sulfide minerals, and how we control the heat generation in the reaction shaft. So we have there sulfides which are combustible. We have there inert minerals like silica for fluxing iron oxides, which is not combustible, and then we have minerals which will be decomposing and needing energy not just for heating up, but also for decomposition. And those materials must be well mixed and divided well and evenly over the cross section of the reaction shaft. And this kind of unit called concentrate burner is doing the job. It is mixing gas with solids and distributing that suspension evenly and in right proportions over the reaction shaft. So this is the key instrument in flash melting furnace or flash converting furnace. If this is not operating properly, your process is not following the needs of your kind of instructions. And it starts essentially from bedding and feed mixture preparation, and that must be properly made. Drying must be properly made, and then weighing of raw materials into the burner and flash melting furnace must be properly made. So it's a long line of things on top of that knowledge of chemical and mineralogical composition of your feed material you are introducing to your furnace. Stable matte grade is not achieved without those issues, following those requirements and needs. So in this sense, flash melting is advanced technology, which means that you must know what you are doing. Let's go for a while to the fluxing chemistry of copper making, and this is an issue where you must take into account your raw material and your processing conditions. All copper smelters in the world use iron silicate slags, and in this issue today we can use thermodynamic simulations for forecasting what's happening in the flash melting furnace, because that furnace is actually acting and operating close to thermodynamic equilibrium in the settler. An exception of that is the entrainment of matte, which is not actually to large extent taking place in the settler, but close to the tapping holes where material streams entrain the other phase with it. So iron silicate slags are used in copper making because they by nature allow high primary recovery of copper, and there are practically no additives in normal operation that are needed for doing the job. One issue, however, is important in running copper flash melting and copper smelting in general. It is the issue of magnetite content of slag. Copper smelters are following the oxidation degree of their smelting charge by sampling and measuring the magnetite content of the slag. So it is giving an indication of ferric oxide content of the molten slag. There is no solid magnetite in the smelting furnace, but it precipitates very quickly out of the slag when the slag is cooled. And that is why, and because magnetite content is very easy to measure, so magnetite content is used as indication of the oxidation degree, but it's not only a constant. It depends on the silica content of the slag and temperature. This is a plot of actually of nickel smelting case, but the slag is similar to copper, showing how ferric oxide content is changing as a function of silica content of the liquid slag, and parameter here is temperature. So what is happening if we are increasing silica content of the slag? The ferric oxide content is getting smaller and smaller, and magnetite content is going down. So if you compare magnetite contents of different smelters having different fluxing practices, you are comparing bananas and apples. So you need to know what is the operational point in matte, in terms of matte grade, and also in terms of slag composition before doing any conclusions in there. So we may have gangue minerals which are modifying our slag chemistries, and we may have raw materials which have such elements which are changing the slag assays and the slag behavior. Typical oxides of this kind are alumina, typically coming many future smelters from e-scrap, so electronic scrap. We may have magnesia from magnesium-bearing silicates in our gang, and we may have too much silica, which must be fluxed by lime additions. So these three common oxides are modifying the slag chemistries, and variable raw materials, which may not be the Indonesian case, but very common in custom smelters, may raise challenges in the fluxing chemistry from operational point of view. So for this purpose, we have nice modeling tools which can be utilized, but in certain cases and new kind of modifiers, slag modifiers, there may be cases where fundamental data are needed before we can do those simulations in details. Now I will talk about trace elements and their behavior in flash melting, because they are often very valuable in copper metallurgy, and the focus here is precious metals, silver and gold, and platinum group metals, which in most cases are not so common in copper sulfide raw materials, but may become important in cases where various electron scrap materials are used as raw material in flash melting. So we have measured the behavior of these elements in flash melting type of conditions in Aalto University, including fire refining slags in presence of metallic copper. And I will now show you a couple of examples how these elements behave in flash melting, so matte slag equilibria. All these metal losses are caused in all cases, including precious and platinum group metals. They are caused by oxidation of metal from matte into the slag, and this is in spite of low stabilities of silver and gold oxides. That is what has been proven by experiment in the literature. And here we see solubilities of silver and platinum in slag from 1% concentration in matte, and these have been measured experimentally as a function of matte grade, so and temperature, and we see that at a typical 65-70% matte grade, solubility of silver is around 50 to 60 ppm by weight, which is rather high concentration. And platinum concentrations in similar conditions are much lower. They range from 1 to 2 ppm parts per million by weight. So this is the primary data of such experimental observations, and what we do to generalize this primary data is that we use distribution coefficients to reflect the thermodynamics of these elements in both the matte and slag. These distribution coefficients are useful in industrial use as well because they are fully independent of the scale. So they are defined as the ratio of the element, trace element in mud divided by the trace element concentration in slag. And these can be basically obtained and calculated from industrial assays of the smelter as well, if the accuracies of analytical devices allow. So in case of gold, this distribution coefficient from those previous series of measurements at max grades of 65 to 70% copper, they are over 1,000. So this is logarithmic coefficient. They are from 2 to 3,000. And in case of palladium, even higher. So more than 4,000. So this means that even in smelting cases where low-grade copper matte is produced, the distribution coefficients of platinum group metals and gold, they are extremely high. And this means that the primary recovery of these metals is more than 3/9. So 3/9 of 99.9% going into matte at smelting temperatures. And this is actually meaning that what you must be careful with in matte smelting is the entrainment of matte in your slags, because most of platinum group and gold losses occur in the form of that entrained matte. So it's clearly calculated from that distribution coefficient itself. So those measurements were calculated in laboratory conditions and with pure iron silicate slags at silica saturation. So in industrial slags, we always have small amounts of alumina, magnesia, lime, potassium, soda, and those basically are increasing the distribution coefficient. So they are even better with small amounts of these slag modifiers in the slag. So the online availability of a smelter is the key for making money. So in flash smelting, this online availability is meaning that all these auxiliary equipments are operating properly, and because it is one line, one pipeline, the reliable operation of each step is contributing into the reliability of the smelting line, and thus increasing the online availability of the smelter and tonnages smelted and processed at the site. So I shortly go through now with issues related to the off-gas line, because those are seldomly discussed in any textbooks or in the literature. So why the gas train is important in terms of the online availability? It is because of the flue dust mostly. And this uptake shaft, which is connecting settler with the heat recovery boiler is the first part of the flue dust management. There we oxidize all sulfidic particles which may be present in the flue dust. So adding controlled amount of oxygen from here, so sulfides are oxidized, and that is important for the next step of the flue dust management, which is taking place in the heat recovery boiler. And this heat recovery boiler is a big hollow device where oxygen is added to the cooling of gas, and it causes, when temperature goes down, it causes some oxides to be converted in sulfates. So heat recovery boiler actually was introduced in fast melting line for capturing the heat values, which it converts into steam, and that steam can be used basically for heating purposes, frying the feed mixture, or generating electricity to the local grid. But this chemistry, what we do in heat recovery boilers, is equally important from operational point of view. So the flowability of flue dust is ensured by controlling these sulfate forming reactions in the boiler, and those sulfide forming reactions need oxidation of sulfur dioxide into trioxide, which is usually exothermal reaction, and it's a large contribution in the heat output of the heat recovery boiler. So this way we get flowable flue dust, which can be taken out from the boiler. In cases it doesn't flow, it forms accretions and blocks the off-gas line, off-gas train. So volatiles which are reacting and making fumes in the smelting vessel itself, in settler and reaction shaft. So they will condense when temperature is going down, and some elements like rhenium and arsenic don't even condense in the boiler. They end up in the washing section of the acid plant, where typically rhenium in some smelters is recovered. So this is what happens in the excuse me, in the boiler, and contribution to the distributions of volatiles in flash melting. depending on how flue dust is treated. Is it fed back into the slug or treated separately? So this is the key question. Yes, this is summarizing the issues. And I have few words about the last step of the primary smelting or flash smelting, because it is producing slag which must be treated because of copper recovery. So slag cleaning is ensuring the high recovery of copper also in flash smelting. So there are two main technologies: milling and flotation, and EF reduction, mild reduction, settling, and they have some importance in trace element distributions and recoveries, in addition to the copper recovery as well. So the physical characteristics of the tailings from these slag cleaning operations are different. Milling and flotation will give very fine silt, which is useless in reusing elsewhere, whereas cast blocks of slag or gravel may be used in construction purposes in civil engineering. The difference in these two methods is that milling and flotation gives a better recovery of copper, so that tails in flotation may be containing only 0.25 or 0.3% copper, whereas EF cleaning is always close to 1%. So this question of the efficiency of the smelter. And what is important in terms of these trace elements is the reaction which is occurring during the solidification of the slag in milling and slag cleaning, milling and flotation processes, where iron oxide, so ferrous oxide and copper oxide dissolved in slag react, forming magnetite and metallic copper. And this metallic copper dissolves weakly bound metals from the slag during that slow cooling process. Typically arsenic, antimony, which are then recirculated back into smelting together with the slag concentrate, and this has an impact on the behavior of harmful and also useful trace elements in copper smelting. Okay. Now I think it's Imam's time to continue.
Yes. Thank you, Pekka.
Yeah. Please. Yeah, the second presenter would be Mr. Imam Santoso. He is the lecturer in ITB currently. Pak Imam will presenting the third and the fourth part of this presentation. Time is yours, Pak Imam. Monggo, Pak.
Okay. Thank you, Bang Erika, and thank you, Pekka. Actually, the expert is Pekka, Bang Erika. I'm just his student, so hopefully I can present very well today, because it is a lot of expert here. I see there's also Pak Durban joined and many other experts of copper smelter in Indonesia. And I hope also everyone doesn't fall asleep, because I will talk a lot about chemistry, phase diagram. So I hope everyone can enjoy, and I try to make it as quick as possible. Okay, if Pekka produce mud, now it's time to change from mud to copper. And this process is called mud converting process. So we will talk about converting mud, which is a copper, iron, and sulfur mixture, to become copper. And if we talk about converting process, 70% converting process around the world use Pearce-Smith converter. And why this is so popular? Because it's because of two reasons. It is a simple operation, and also it can be fed by a recirculating material such as copper scrap, like that. However, it is good at the same time that it is simple, but Pearce-Smith converter is a batch process. It needs very skilled operators, and also because the process control development of Pearce-Smith converter is very slow, so it really depend on the skilled operator. And another disadvantage of Pearce-Smith converter is that it's produce gas flow that contain very low in sulfur dioxide. And then this is the process in mud converting using a Pearce-Smith converter that operator undertaken in a control room. First, the mud is charged to the Pearce-Smith converter. The converter is a bit tilted, and after that, we introduce oxygen or blowing process. And after that, when slag is formed and iron already removed, then we skim that slag. Basically, this is the three main process like operator undertaken: charging, blowing, and skimming. And then this is the main development of Pearce-Smith operation. I will talk about what this is. I mean, there are a lot of research, but the main research in here in Pearce-Smith converter is mainly control is still very limited in Pearce-Smith converter. And then, okay, next, what is the reaction? What happened in converting processes? And in converting processes, because we want to change, because we want to convert mud to become copper. So this is mud. We want to change to copper by introducing oxygen and also silica as a flux. And there are two main reactions. First reaction is oxygen react with iron, producing slag. And the second reaction is the reaction of oxygen with copper sulfide, producing copper and gas sulfur dioxide. So the first reaction is called slag blow or slag making process. And after that, after the iron is removed or going to the slag, and then it's now time to blow to produce copper. So it is called copper blow. So this is like two main reactions that have to be remembered. And then, okay, this is the phase diagram. I hope everyone still remember what they learned long time ago, maybe long time ago. Pak Sunara or Pak Rojik taught this phase diagram. And right now I want to talk a little bit about slag chemistry in converting process, because in the slag blowing, the first step of the converting is removing the iron. So it is called slag blowing or iron blowing. So it is important to see the phase diagram of silica in the top corner, and then wustite and also hematite. Because iron in the slag can be formed as magnetite also. So this ternary diagram is very good to describe the situation that happened in the slag. And the blue line here is describing the oxygen pressure in the system. So when it is moved to the right, the oxygen pressure is increasing, or if oxygen pressure increasing, it means the condition is very oxidizing, right? For example, in here, the oxygen pressure is 10 minus 3, it is very oxidizing, but in the left, it is less oxidizing. When we want to produce good slag, it means the slag have to be very liquid or to be liquid. And this is the liquid area of the liquid slag. And the second thing is that we need very oxidizing condition. Why? Because converting is oxidizing process. So if the condition is very oxidized, and then I can remove a lot of iron. So the most oxidizing condition then is point A. In point A, we still have slag, and also the oxygen pressure is high. If we use oxygen pressure, for example, in here, -3, we don't have liquid slag anymore because the slag is in here. So the indication when the process is good, we can see from the slag that contain silica and magnetite, because point A is a slag in saturation with silica and magnetite. Okay, so before, I mean, in the end of the iron blowing or slag blowing, usually we will have, or the slag composition is little bit under the point A. So if the slag is under point A, it is in the saturation with magnetite. So, so before the process is moved to second step, which is copper blowing, the slag blowing can be seen that it is already finished by the saturation of magnetite. So usually the slag that describe the end of slag blowing will have magnetite or slag with saturation with magnetite. This is the point of magnetite. Therefore, in a converting process, the slag is controlled to have value with iron and silica ratio around 2.04. So again, because iron in the slag can form as Fe or magnetite or rustite, so we just use this iron divided by silica have to be bigger than 2.04 in order to get the optimum conditions. And also these conditions will allow us to have very good slag. This slag also will can form freeze lining on the brick lining. So the slag also can be very protective to the brick. So the operation or the shutdown of the furnace can be delayed because the brick will have can run longer, because if the slag can be formed in the operation, it can form protective layer for the brick, so it can protect the brick from the aggressive attack of the slag. However, in some concentrate, like in Indonesia, the concentrate can contain alumina and also soda, and this will also affect the stability of oxide. For example, we can see here that when the potassium or alumina exists in the slag, it can enlarge the liquid slag area. You can see here, and also the point A where the slag and silica and magnetite is saturated, it moves upwards, or in other words, that the slag area become more wider. So this is the more or less the effect of the potassium and alumina to the chemistry of the slag. So the red line is when the slag doesn't contain any potassium or alumina, or it is pure iron silicate slag. So we can see that the stability of the slag again is become larger. And in addition to that, when we decrease the temperature, the liquid slag area also becomes smaller. So we have done a lot to get the optimum condition in the converting process. It is temperature, it is also impurities. Okay, we just talked about the slag chemistry in a converting process in a slag blowing. So basically, this is what happened to the mud. We can see here, we have concentrate. This is ternary diagram of copper, sulfur, and iron. The concentrate, the location of concentrate in the ternary system is in here. So point A is a chalcopyrite concentrate. So more or less the concentrate located in this blue cycle concentrate. So when it is melt in like flash smelting process, so the concentrate composition will move from point A to point B. We can see here during smelting from point A to point B, the copper concentration is increasing and the iron concentration is decreasing. So basically during mud smelting, we're removing iron and sulfur. And from B to C, this is converting process in the first step, which is slag blowing. So during slag blowing, the concentration from B move to C. In C, we don't have any more iron, or the iron is very, very small. So during a converting in the slag blowing process from B to C, it is clear that we are removing almost all of the iron. So now we are in the location of binary copper and sulfur area. So again, actually smelting and converting, we can describe the mud composition in roughly in the binary FeS and CO2s. And after that, from point C, we still have a big content of sulfur here. In point C, the copper content is around 80% and the sulfur content is around 20%. So we need to remove sulfur right now. And the process then moving from C to corner of copper. And this process is still converting, but the second step of converting, which is called copper blowing. So I already described this one, and now this is the copper blowing. In copper blowing, after almost all of iron is removed, we are now in the point A. In the point A, we see that the sulfur is around 20% and the copper is around 80%. So during copper blowing, we remove the composition of, or from point A to point D. Point D is almost pure of copper. So this is basically the process of converting. And then because we introduce oxygen to remove sulfur, and of course there will be some amount of oxygen dissolved in the blister copper, and this oxygen will be in equilibrium with sulfur dissolved in the copper also, and in equilibrium with sulfur dioxide. And we can see here the relation. If we want to remove more sulfur, it means we need more oxygen. It means more oxygen will be dissolved in the copper, and therefore, when the sulfur is reduced a lot, very low concentration, at the same time, the oxygen concentration will be high. This is the example. The concentration of the sulfur and the oxygen in the relation with oxygen pressure at different total pressure. So we just talked about the converting process in Pearce-Smith converter and also the reaction that happened in the converting process. Right now, we will talk about the flash converting process. So if we use Pearce-Smith converter, we will need this 3 reactor. This is Pearce-Smith converting reactors. So if we use flash converting process, we don't need any more this Pearce-Smith reactor. Now we need a flash converting reactor. The shape and the design is almost the same as the flash smelting furnace. So we can see here from the diagram that mud from the flash smelting furnace is granulated, and after being granulated, it is a grind, and after it is grind, it is fed to the flash converting furnace. And also the same, the reactor or the process is also autogeneous, and the enriched oxygen gas is used here because we use enriched oxygen gas. The gas the ratio between mud introduced to the furnace with the oxygen. So the gas flowing out from this furnace is continuous. It will going again. The gas here will have a process. And this is the comparisons between flash converting process and Pearce-Smith converter. The gas emitted from the flash converting furnace is smaller. You can see here per ton of this is for the same basis. It is per ton of blister copper process. So we can see here that Pearce-Smith converter will produce almost 100,000 normal meter cubic per hour of gas, but flash converting, it is only small amount. Because it is small amount, of course, will be extended. We can see here when it is used Pearce-Smith converter for converting process, it will consume a lot of bricks. So it means the lifetime of the bricks when it is used Pearce-Smith converter is shorter. It is need to be mentioned that the process in the flash converting reactor need to be maintained to be steady, no fluctuations, because constant operations, and therefore the mud that is fed to the flash converting process need to be very homogeneous or almost the same in concentration. Therefore, it is need to be controlled in the flash smelting furnace because the mud that is fed in the flash smelting furnace need to be homogeneous. It means the mud produced from flash smelting furnace also needs in the flash smelting furnace. And how to control like mud in the flash smelting furnace, maybe Pekka already mentioned, we can control with the oxygen coefficient. in flash smelting furnace, the variation of the oxygen coefficient can be 20% because the concentrate can be varied a lot. It's come from different supplier around the world. So the flash smelting furnace, the operation can accept that. The operation can be vary around 20% the oxygen coefficient, but it is different with the converting flash furnace that need to be very steady the operations. And in here we can see if the mud, if the copper in the mud is very low, for example 28%, of course it will need more oxygen to make the same mud grade, for example 70%. But for if the mud already have a high grade of copper, say 32, so it need less oxygen. So now the converting process produce blister copper, but the blister copper itself, we can see here, it still have a very high content of sulfur. It is around 0.1 until 0.05 in terms of sulfur, and the oxygen it can be 0.1 until 0.8%. The sulfur and oxygen is still very high. Therefore, now the copper, blister copper from the converting process need to be refined, and the process for the refining of blister copper is called fire refining because we use oxygen. So we use oxygen again, and we can see here after first oxidation, because we use oxygen, we will see later, the sulfur is reduced from 0.1 to 0.02. However, at the same time, oxygen increase. Why? Again, because when we remove sulfur, we introduce oxygen, and therefore, in the fire refining, we still have similar like in the converting process. We have two steps of the refining. First, we are removing sulfur with oxygen, and the second step, we are removing oxygen with hydrocarbon. And this is more or less the reactor of the anode furnace. There is a charging mouth here, and then the oxygen will be blown from the bottom. And this is the typical picture of the real anode furnace in Aalto. And again, this is the same relation. When we have very low sulfur content in the copper, the oxygen will be very high, and thus we need a two-step of process. So this is the reaction mainly. Firstly, we removing sulfur, and after that, with oxygen, we removing sulfur with oxygen, and oxygen will be dissolved in the copper, and after that, we are removing oxygen with hydrocarbon. Okay, now is again Pekka part. Pekka, you can continue.
Yeah, before continue, Professor Pekka and Pak Imam, we do have 10 more minutes for the presentation.
Okay.
Thank you.
Let's go to the future trends and possible needs of copper smelting in future. Forecasting future is always a demanding task, and that is why I will only show you some well, personal ideas or so on, which are rather evident at this point of view. So the visibility of future is not very long, not anywhere, or not in any subject, and it's not so in copper smelting either. So I will concentrate on a few things which are, and meaning that raw materials are the challenge in the future, and I will give you some ideas of the future kind of trends in process control issues as well. So complex concentrates are and must be taken into use in the future because of ever-growing demand of metals, and that means that we will face two types of raw materials which have been coming gradually, but they will be more so in the future. And the one issue there is that the grades of valuable metals are lower because of this complexity. And then we will see new elements coming into our copper smelting circuits. So some are harmful, some are valuable, and some are in short supply in the future world. So flash smelters generally are like in your case, large capacity processing units which allow very high feed rates and very wide and extensive raw material mixtures once you know what to do. So what are the challenges then and the big one, which is not secret to anyone today, is that we are generating in the world, this statistics is from last year, so 7 kilos per capita of waste which is regarded as electronic or electric equipment waste, and 7 kilos per each person on this world, and that means that there is a huge amount of valuable metals and existing smelters of various types, including copper smelters, are the suitable processes for treating and recovering those metals. So e-scrap is also today the fastest growing waste in the world, and it contains large amounts of copper and precious metals, and this is something we must keep in mind and take into account when we are forecasting also copper smelting. So this means that new elements from electronic scrap is coming to the smelting circuits, and we need to ensure that valuable things like precious metals and platinum group metals are recovered. But then there will be also elements we don't see today in copper smelting circuits, like indium, gallium. Well, that tin is not common in copper smelting, but it is there in certain ore bodies, and this kind of small metals which are in short supply in the world. So they must be recovered, and they must be taken out, even if their concentrations are low. And how to do that, we don't know yet, but that challenge will be faced by us very, very soon. Battery materials are the big group of new materials. Some of them can be smelted in copper together with copper concentrate, some of them not. Then artificial intelligence is an issue in all processing branches for materials, and that means that we will see various applications also in flash melting, which are based on digitalization and digital tools for monitoring the processes, intelligent control, and for various online offline simulation purposes. So we know that there are new control devices and observation possibilities for the flame concentrate combustion control in flash melting reaction shaft, and those will be improving performance of the smelter and increase the online availability, and these also mean that because they can be used as offline simulators, so they will provide increased skills for the staff and operations, because they can be used for simulating the cases which are not wanted and dangerous, which are dangerous in real operating smelters. So these process advisors are on a routine basis used either as offline aids, or even in some cases as online controllers for smelting in flash smelters. And to summarize, I think I will go into this last slide. What are the benefits of using flash melting technology? So the high production availability and large tonnages, which count in many copper smelters, in particular in custom smelters. So high recoveries of copper and side metals, typically gold, good energy efficiency, low emissions, and also efficient use of water and efficient waste management, and which is not minor thing as either is the security, safety, and health issues in flash melting. So I think this was what I had in mind, and now I hand over to Imam for his final words.
Okay, now is my part to conclude this presentation. Flash melting furnace and Pearsmith converter are two new technology in Indonesia, I think, because right now we only have like Mitsubishi continuous process. So flash melting furnace and Pearsmith converters will be new in Indonesia. The both process have their own specific feature, which must be understood and followed. And flash melting furnace is sensitive technology where many operational features are interlinked. And also Pearsmith converter is a batch process, need experience and skill operators. And also this is the one of the very important, that university cooperation, even partnership and continuous education of staff cannot be emphasized too much when building the national knowledge bases. It means like if we want to build the national knowledge basis, technological know-how and also business know-how, we have to know that everything has to be in here in Indonesia. So thank you.
Okay, thank you very much, Professor Pekka and Dr. Imam, for the presentation. It was a great presentation from both of you. During 6 section of the presentation, we have noted several, interesting topics, starting from introduction to glass smelting and its history, which is invented in 1940s, and then why it's this technology is, become a leader for about 70 years because of the continuous development, capacity, reliability, auxiliary, as well as in the technical side, it's over the high sulfur capture. And then in the matte smelting in FSF, we do have the concept of FSF. We noted several concepts of FSF, glass smelting furnace. And then in the matte processing in PS, Pierce Smith converter, as well as the glass converting furnace. We do have the, the comparison between the two, also as the AF fire refining. And also we do have the future trends, needs in glass melting, and the concluding words. I think it was a good presentation from Professor Pekka and Dr. Imam. Now our turn to open the questions. We do have first questions from Marco from Metallurgical IAMETITB 2006. The questions: what is the advantage of flash process compared to Mitsubishi process? So that is the first question from Marco.
And also someone raising hand, Bang. Gustama Amanusa.
Okay. Let Pak Gustama Amanusa to speak. Pak Fikri, can you unmute Pak Gustama for the questions?
Yes, already, Pak.
Okay, thank you for the opportunity. Good afternoon, Professor Pekka, and good evening for all of the audience. My name is Gustama. I'm one of the Mas Imam students. I want to ask a few questions for Professor Pekka. It's been said that magnetite composition in slag matte smelting is required to as an indicator that oxidation does well. But I read that magnetite composition make the slag become viscous and it's harder to being tapped. So how much is the composition of the magnetite is optimally should be there, Professor Pekka? Thank you very much.
Yeah, that's a good question. So magnetite as such in homogeneous slag is not making the slag viscous. But if you have suspended solid matte particles in your slag, so if the slag is saturated by magnetite, so then you end up with viscosity increases. So this is the case. So magnetite content, as I showed in one of my early slides, is generated by the smelting, and in matte making, it is depending on your alumina, lime, and magnesia content, and depending on the matte grade, it's around 15% magnetite in the slag. So it's generated by itself. You can't control it by any means, except by adding silica. But there is also maximum fraction of weight % of silica you can introduce in the slag. And what is probably more important, when you increase silica content in your slag, you are increasing the slag volume, and that makes more complicated because you are actually you are actually increasing your copper losses to that and so on. So there is no optimum value because it depends on your fluxing practices and your raw material gang compositions. But it's between 10 and 15% in normal operation.
Okay, Pekka, the question about the advantage of the flash smelting process comparing to Mitsubishi.
Yeah, the second question would be from Marco, Pak Marco. The question is, I mean, the first three questions will be will be read, and then after that, we would like to Professor Pekka or Dr. Imam to respond. The question from Pak Marco is advantage of the flash process compared to Mitsubishi process. And then the third one, the question from Pak Arif. Pak Arif is questioning about the nickel smelting by FSF, flash smelting furnace, as he has ever seen the smelting of nickel sulfide concentrate by FSF in Jinchuan. The question would be, is it possible to use FSF system to process nickel oxide, or especially limonite on the type of either calcine or concentrate producing ferronickel metal? If it is yes, therefore it will be a better technology choice to utilize huge of limonite here in Indonesia instead of using the HPAL. So those two questions probably can be answered by Professor Pekka and Dr. Imam.
All right, about the comparison between Mitsubishi operation and flash smelting operation. So I'm not very familiar with Mitsubishi's details, but my general impression is that designing a big smelter using Mitsubishi technology, bath smelting of sulfidic concentrates, it has not been possible for one reason or another. And to my understanding, that reason mostly is related with the heat dissipation from the smelting furnace. So I have seen in Timmins, Ontario, the Mitsubishi furnace, and they were feeding, that's closed now, but they were feeding slag, granulated slag into the smelting furnace in order to increase the capacity, but it is perhaps the dissipation of heat in a bath, which is the limiting step in that process. But that's just my personal opinion. I haven't analyzed it in more details. When in comparison with flash smelting, as I said, the capacity increase in almost same size of furnaces is tenfold in flash smelting. So the first furnace in Harjavalta was producing 20,000 tons of copper a year, and today they are producing 200,000 tons of copper, so 10 times of the original, and it is due to the oxygen enrichment in the process gas, but also indicates how well heat can be dissipated from the suspension, gas solid suspension, in the reaction shaft within very, very short time. So this is the fundamental difference in all bath smelting processes and suspension smelting. And I think the kind of core thing is there. Why bath smelting processes? There is no big smelter based on bath smelting in the world. They are all flash smelters.
Okay, hopefully it answers the Pak Marcos questions.
And
You can continue.
then this limonite oxide, nickel oxide issue. So limonites, like the other laterites, are very, very lean in nickel. So and nickel is in oxidic form certainly in there. So it doesn't have any energy value. That means that you are not you cannot smelt limonites in the same way in flash melting furnace, because they don't generate heat. You need sulfidic nickel concentrates with concentrate which may be mixed with limonites, but that's a marginal. I don't believe that is possible because of this mismatch between lateritic nickel ore bodies and sulfidic. So sulfidic nickel ore bodies are much rare in the world, and most of the nickel deposits are lateritic in the world. So yeah, that is a question which has been asked also earlier, because your neighbor country Australia has also this kind of lateritic nickel deposits, and to my understanding they are not used along with flash melting in Kalgoorlie now at this moment. So it's a good question and big challenge, but at the present time I don't see any practical kind of options how to do that.
Okay. All right. Thank you, Prof. Pekka. Dr. Imam, do you have any additional comments to respond to these two questions?
I think Pekka already answered very well. So we can't extract the nickel oxide with oxygen. So oxygen meet with oxygen, it will not extract. So it cannot be done because in flash melting, the heat is generated from the chemical reaction and the heat is used to smelt. So if we react oxygen with nickel oxide, nothing will happen. NEO plus oxygen is nothing happen. So it will not produce heat to smelt. So it's impossible. But I don't know, Pekka, maybe we add sulfur because we have mountain sulfur in Indonesia and we use sulfur as the energy, but I don't know. But it is not possible, I think, if we use in the same way as flash melting to smelt nickel laterite, I think. But
So
if it is nickel sulfide, yes, it can. If your ore is nickel sulfide, yes, it can. Thank you.
Okay. So the key thing is generating the heat, yeah, from sulfide.
Yeah, that is the key.
Okay. All right. Let's go to the next questions. The first question is from Putri. Ms. Putri was saying that, you know, on the presentation, there's a lot of advantages of the flash smelting process, right? The question was, what is the limitation or disadvantages of this flash process? Is there any limitation on this process? That is the questions. And then the second question of this, you know, batch is from Muhammad Iqbal. Several sources saying that flash smelting process can be adapted to the nickel smelting. And the question is, what is, I mean, the process nickel smelting in the FSF, is it the same advantages as well as, you know, as compared to the copper smelting, compared to the electric furnace, if let's say the FSF is adapted in the smelting, the nickel smelting process? I think those two questions probably can be responded, Prof. Pekka and Dr. Imam, before we go to the next question.
The first one dealing with weaknesses or weak points in flash smelting is an interesting question. From technical point of view, there is no issues I would think as drawbacks or problems in using flash smelting for any concentrator in copper making or any size of the smelter. But in practice, all the big smelters in the world, they are flash smelters, and other technologies are used in small smelters, and this is a question of many things which include environmental issues and local legislation and so on. But to my understanding, the flash smelting concept can be used and has been used in very, very small smelters, less than 100,000 tons a year copper production. But it is not regarded as economical today. So other technologies which may be more simple and more straightforward and have kind of lower credits in terms of environmental issues are used for very small smelters, 10,000, 20,000, 50,000 tons. So that is what I understand about flash smelting. It's not technological issues, but it's more or less these local needs and environmental regulations and so on. So there are still copper smelters in the world using sulfidic raw materials which exhaust all sulfur in the atmosphere. If that is allowed by the local government, so it's okay, but it's not what I understand with sustainable smelting and sustainable technologies. Then this other one was again about nickel smelting.
Right.
So what was the? Yes.
Yeah, the question was if, let's say, FSF can be adapted for the nickel smelting process, what is the advantage of using FSF for nickel compared to electric furnace? That was the question from Iqbal.
Okay, yes, now I recall. So yeah, if your raw material is sulfidic raw material, so nickel sulfides, pentaldite, biolorite, whatever, nickel bearing sulfides. So the most economic way of doing the smelting is certainly flash smelting. So there is no point of first partially oxidizing the sulfides in the roaster and then using electric energy for smelting that calcine into matte, which is then converted into iron-free matte and further on refined into metallic nickel. So nickel making is much more complicated than copper making because of its kind of characteristic chemical features. But if you really have a nickel sulfide content containing raw material, so So the straightforward, environmentally most friendly way, and in terms of energy efficiency, flash melting is option really available for treating this kind of material. And this new EON, direct autotechnical smelting, which I was happy to be involved in the development in 90s. So it is even more environmentally friendly because it doesn't have Pearce-Smith converters for making the iron-free mat, but it's like direct to blister, but it produces essentially iron-free nickel mat. That kind of operation is in here in Finland and is in operation in Brazil, South America. So yes, if you have sulfidic raw material containing nickel, so flash melting is the only feasible option for utilizing that raw material.
Okay, thank you, Prof. Pekka. Dr. Imam, do you have any additional comments on these two questions?
I think Pekka already answered. Yes, maybe
Okay.
I will comment about the next question about the smelter. Yeah.
I think there's since we do not have any more time, the last two questions, probably one from YouTube and then one from Zoom meeting. The first one from Zoom meeting is from Pak Husin from Gorontalo. Nowadays, a lot of investors to have a plan to build the copper smelter in the area eastern of Indonesia, or and then what is how the smelting to be that is environmental friendly? That is the questions, first one. And then the questions from YouTube, for your information, we do have a live in YouTube as well, and several, I think more than 10 people is watching as well. The questions from the participant in YouTube is one: where is the highest capacity flash smelting furnace in one line that has been operated in the world? And then the second one from Pak Irawan through YouTube: one challenge in using flash smelting furnace is the capital cost is very high. What is the typical capital cost per ton copper cathode for this flash smelting furnace? That is the questions. Please, Prof. Pekka and Dr. Imam.
Maybe I will answer the easiest one, Pekka. The easiest one is about the environmental issue. So
yeah,
if you want to make the copper smelting process is good for environment, so it means we have to process the off gas, and the most of the copper smelting process that use flash smelting technique, or even Mitsubishi, they produce a high sulfur content, so it have to be processed like for sulfuric acid. So the smelting company will get money, not only it's emit less sulfur, it means it is very good for environment, it also can get money from the selling of sulfuric acid. Thank you, Pekka.
yes,
Thank you,
probably
Dr. Imam.
these two other questions, I'm not sure about being the right person to tell anything about the commercial issues of smelter designs and their costs. I'm not touching that, but the question of the biggest single flash melting furnace, I think your new furnace will be within top 3 in that. So I know that we have at least 2 or 3 furnaces which are on the same level of production at the present time. but I don't have the exact and accurate figures with me now. So at least I'm sure that this was what was mentioned earlier. 550,000 annual tons of annual production of copper. It is within top 3 in the world.
So meaning that one line capacity processing 1.6 million concentrates to produce that copper cathode, Prof. Pekka? Or what is the highest concentrate process in one line?
Well, it's increasing. It's increasing all the time, but I don't know. I rather talk about the tonnages of produced copper because I'm not mining man, but mining people often talk about tonnages of processed copper concentrate. So concentrate grade is sometimes much lower than this 30% you have there in Gresik and other places. So tonnages of feed may be larger, but production wise, this 500,000 tons of annual cathode production is really high.
Okay, all right. I think in our Zoom meeting we do have Pak Jeki Sham, who is a very experienced in the Autotech flash smelting. Pak Jeki, do you have any comments on this, Pak?
Yes, thank you, Pak Erika. Assalamualaikum semuanya. Pak Pekka. So just wanted to help you guys with the capacity. I think the largest one in the world now is one line, and of course, it meant to be your flash furnace, Pak Erika. Freeport will be the largest one in the throughput side. But now, as far as I understand, it's about 400,000 tons capacity, cathode capacity per year, about 400 to 440. That's in China.
Yeah.
And what about the typical capital cost, Pak Jeki, from your knowledge, based on your experience?
I think because that's depend on a lot of things, I prefer to discuss that in the different opportunities, Pak Erika. Sorry
Okay,
about that.
All right. Okay, Pak Jeki, thank you for
Okay.
the additional comments, and I think that is very helpful for us. I think it is.
Bang Erika,
Yeah.
so if you build the smelters next year, you will process like 2 million ton concentrate per year. So it will be the biggest flash smelting plant in the world. That's true?
I think so.
Correct, Pak.
Okay, good.
All right, but I think that is not in this forum, yeah. we can discuss in another forum. All right, I think this is very interesting presentation and discussion. However, our time is limited, and based on my laptop, timing now is 4 p.m. 6 minutes past 4 p.m., which means that we can conclude our presentation and discussion this afternoon. I think we do all agree that this presentation is very useful for us. And thank you, Prof. Pekka, thank you, Dr. Imam, for sharing us the flash smelting furnace, as well as the flash converting furnace, as well as the Smith converter. We do believe that what you have been presented, it will, beneficial for us. And I think for the questions that cannot be responded today, we are going to summarize the questions, and then will be delivered to Prof. Pekka and Dr. Imam to respond later, and we will distribute through email. again, thank you, Prof. Pekka, thank you, Dr. Imam, for sharing the information. And I think before we can conclude this webinar, please everyone to to turn on the video, because we would like to take a picture. Again, thank you for everyone joining this presentation. Hopefully, we all still have a question about the topic for this, this afternoon. Jadi sekarang kita coba taking picture, Bapak Ibu semuanya. Terima kasih untuk partisipasinya. Silakan Pak Fikri untuk memulai.
Oke, untuk slide pertama saya ambil print screen-nya. 1, 2, 3. Baik. Kemudian untuk yang kedua, 1, 2, 3. Dan yang terakhir sepertinya yang ketiga. 1, 2, 3. Baik, cukup Pak Erika, saya kembalikan ke Pak Ik.
Baik, terima kasih Pak Fikri. Bapak Ibu sekalian, terima kasih banyak atas partisipasinya pada sore ini. Kita akan kembali bertemu 2 minggu mendatang dengan topik yang berbeda dan tentunya akan juga selalu menarik untuk disimak. Thank you again, Prof. Pekka, for your presentation, Dr. Imam, for your presentation as well.
You're welcome. You're welcome.
Hopefully, it is not the first one and the final one, so we will have another webinar. Thank you all.
Thank you.
Good afternoon
And Pak Imam.
Selamat sore. Assalamualaikum warahmatullahi wabarakatuh.
Thank you. Terima kasih. Warahmatullahi wabarakatuh. Thank you.